Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. Doug is the Frank M. Mather Professor of Computer Science and Director of the Center for Human-Computer Interaction at Virginia Tech. He is the Principal Investigator for the 3D Interaction Group, which focuses on topics of 3D user interfaces, VR, AR user experience, and the benefits of immersion in virtual environments. He served in many roles for the IEEE Virtual Reality Conference, including Program Chair, General Chair, and Steering Committee Chair. He's also co-funded the IEEE Symposium on the 3D User Interfaces. He's received a career award from the NSF for his work on 3D interactions and has been named an ACM Distinguished Scientist. So thank you, Doug, today for taking the time to come talk to us about your work, and I'll go ahead and turn the time over to you.
Great. Thanks, Sarah, and thanks everyone for being here. Thanks for the invitation, especially Hai Chao for hosting. I'm really excited to be here and to do this talk, and also have interesting discussions over the next couple of days. Thanks to everybody online for being here as well.
Cheers.
Perfect. All right, so I'm going to talk today about VR, about virtual reality, and really kind of answering what in my career has always been like the biggest question about VR, which is it really worth it? Is it more than just a cool, flashy demo? Is it more than just a toy? Can we use it for real applications in which we do real work? And can we demonstrate that it has benefits for that over other technologies? So, just to kind of start and set the stage, I mean, obviously, I think everyone is aware of VR these days. When I started in the field back in the 90s, I still had to explain pretty often, like, what is this thing and why should I care and so on. But, when companies like Sony and Meta and Apple pour billions of dollars into a technology, everybody in the world sits up and takes notice. So it's definitely a mainstream technology these days. However, I would say there's still a lot of people who have not used the technology. Certainly a ton of people who have not invested in the technology for themselves, whether at home or at work. And when you look at the applications that are the most prominent today of VR, they're still kind of the things that you would expect that are money makers. So it's games, right? I think probably still the most popular VR game of all time is on the left here, which is Beat Saber. Who's played Beat Saber in the room? Yes, good. Okay, everybody in the front has played it. That's good. My kids love it. It's good exercise and a lot of fun. But it's an entertainment experience, right? You're not getting anything really productive done in there, except maybe you burn some calories. And on the right, I'd say the other most popular category of applications is social VR, right? So getting online with your friends, or you're meeting new people, and meeting together in a virtual space, and you can dress yourself up in any sort of crazy avatar that you want. So those are kind of mainstream uses of VR these days. Just to kind of put us all on the same page, I want to give my definition of what VR is and some other related terms. So I always say that a VR system is just something that displays real-time interactive first-person 3D worlds. And it's obviously displaying those to users, one or more users. So that's a pretty low bar, right? Any sort of 3D game that you play on your phone or on your PlayStation or on your PC fits this definition, right? So I count all of those systems as VR, but they're not immersive VR, right? So immersive VR is another step up, and immersive VR is just where we employ different, more advanced display and interaction technologies. So we have a stereo display instead of a mono display. We have head tracking, so you can get different views by making natural head movements. We might wear the display on our head, or we might have displays that surround us in space, so we get the sense of being inside the virtual world, right? So the whole idea of immersive VR is to increase the realism beyond what you experience on your phone or your PlayStation, right? And then I'm going to talk a lot about immersion today. So immersion, my definition is that it's the objective level of fidelity. In other words, the realism of the experience produced by a VR system. And there's really a continuum, right? So it's not that we have some things that are fully immersive and other things that are not immersive at all. It's that we have a level of immersion that explains the realism of the experience.
Can the audience mute remote? We get some noise. Thank you.
Thanks, Timo. All right, so coming back to the question of like, what is VR good for? I think there's a set of applications that are fairly obvious. If you think about kind of the experience that VR produces, this experience of being immersed in an environment, maybe with other people, and producing this kind of psychological feeling of presence, a feeling like you're there in this other place that you're not physically in, and that you're there with other people who are not physically in the room with you. And so we already talked about games and entertainment experiences, right? Obviously, those can kind of benefit from this sense of presence because it goes beyond, right, what you experience on your phone or on your PlayStation, right? Now you're no longer like looking at Mario driving the cart on Rainbow Road. Instead, you are Mario driving the cart on Rainbow Road, and Rainbow Road is all around you, right? So that's an obvious benefit. Task and skill training, obviously this is a serious application, right? But it's also fairly clear that if you want somebody to practice a task or to learn a skill, it's better if they feel like they are actually doing the task in the real environment with the real tools, et cetera, et cetera. That's better than watching a PowerPoint. It's better than clicking through a simulation on a PC, right? So that's a huge application that benefits clearly from this immersion in a virtual world. Virtual tourism or cultural heritage, again, this is fairly obvious, right? You want someone to feel like they're in the Roman Colosseum as opposed to just looking at pictures of the Roman Colosseum. We talked about social VR and of course the business application of that, which is virtual meetings. It's better in a meeting if I have the experience of being in the room with the people I'm meeting with than if I'm just looking at their Zoom window on a screen, right? And then a couple that you may not have come across, exposure therapy. This is kind of the idea in psychiatry that if you have an issue like a phobia, let's say, that one of the most effective ways to treat that is to put the person into the situation that they fear, right? And so there's real world exposure therapy. If you have fear of heights, your therapist might take you to a slightly high location, right, and help you to like work through your anxiety. And then if you get past that, then maybe you go to a slightly higher location and so on. Well, of course, we can do this in VR. We can put people in virtual high situations or put people on virtual airplanes if they're afraid of flying or whatever. And this has been proven to work quite well because psychologically you believe that you're in that situation. Your brain believes that you're in that situation. And so that can be less expensive, less dangerous, et cetera, than real world exposure therapy. And then finally, distraction. So games and entertainment experiences are distractions, but that's not what I mean here. I mean things like distraction from pain. So there's been some real success in using VR, for example, in situations where people have serious burns and they need to have their bandages changed on those burns. It's a very painful procedure. If you immerse the person in a virtual environment and their brain is somewhere else, as opposed to in the hospital room where this procedure is taking place, they actually subjectively experience less pain. And so that's a application that benefits from this feeling of presence. So I said those are kind of like obvious applications of VR, and all of them have been successful in various ways. But I want to think about another category of applications, and that is applications where you're in the environment to perform real work that generates real work products that are separate from just the experience of being there or the psychological effects that you get from the experience of being there. And so a few different categories of this, and there are probably more, but I'm mentioning here design and design review, right? So architects and car designers and other sorts of designers and engineers can get into a virtual environment to review the current design, to make changes to the design, to collaborate with others on the design, and so on. And so the result of that is a real world product, right? It's a real world work output. And why would VR be good for that? Well, it's because maybe you can experience the design at full scale in 3 dimensions. You can talk with other people about the design, but you don't actually have to build a mock-up of it, right, in order to do this work. On the bottom here, I don't know if you can see the picture very well, but this is doing basic office work, productivity applications in VR. And I used to think that this was fairly silly, right? Why would I want to just like put my computer into a virtual environment? But there are a couple of reasons why this actually makes sense. So one is focus, right? You can remove all the distractions of the real world and put yourself in an environment that allows you kind of deep focus. But the other is that I have really flexible display, right? So I can make my computer monitor any size and shape. I can place it anywhere. I could, be laying down and working on a computer monitor that's above me, etc. And so there are a lot of people who are doing pretty long sessions in VR just for programming or writing or whatever you do on your computer. And then the last one, which is the one I really want to focus on today, is visual data analysis, right? And that's, I think, of interest to a lot of you. So why would I want to do visual data analysis in VR? Well, the first thing to say is that there's a long history of this. The picture on the left is the virtual wind tunnel. Has anybody seen this before? Yeah, good job. All right. Thanks for being my shield in the audience. So this was back in the 1980s. Steve Bryson at NASA Ames worked on this project. The idea was to do flow field simulations like you would do in a real wind tunnel, to do them in a virtual environment. And of course, people had been doing that on regular desktop computers, but his idea was that if I can get into the environment and kind of see the artifact like the airplane or whatever at full scale, and I can directly manipulate the sources of airflow and evaluate and analyze how that flow interacted with the airfoil and so on, that I might get a better understanding of what's going on and be able to design better aircraft. And so again, that was back in the 1980s. People are still doing this today. Here's a much more recent picture of someone using kind of a modern head-worn display to interact with like I guess this is a protein simulation. But why would you want to do this? Why would you want the user to feel that they were inside the data or to see the data at full scale or fully surrounding in 3D? What good might this be? So here are some hypotheses. So one is that using these technologies, I might get greater spatial understanding about my data. So if I can see the data, not only with 3-dimensional perspective, like you would get on a computer screen, but with stereo, so you get depth separation that's a little better, with head tracking, so you can get a sense of where things are relative to one another as you naturally move your viewpoint around, that you might better understand the spatial relationships, positions, orientations, scales of the parts of your simulation or the parts of your data. Second is that this might result in lower mental workload for interaction. So if you're viewing this kind of 3D simulation or 3D data set on your desktop computer, you're going to interact with a mouse and keyboard most likely, or some similar sort of technology. And of course, you can do all the things that you would do in VR, right? You can move your viewpoint around, you can translate it, you can rotate it, you can rotate the data, you can make the data bigger and smaller, you can select things, you can position probes, all the things that you would do in VR. But that interaction is not necessarily as natural or as directly mapped as what we would do in VR. Because in VR, I mean, first of all, again, moving your viewpoint is just a matter of moving your head, which your brain kind of knows how to do very well from the real world, right? But secondly, even if you're doing 3D selection or manipulation, you can do it directly in the 3D space with your hand, right? Or a tool that's in your hand, which is very different than this kind of indirect 2D mapping that you would do with a mouse. So maybe it reduces the workload, and therefore you can apply more of your mental resources to analyzing the data. And these two together, we might hypothesize, would lead to more rapid insight about the data, more information that you can use for whatever work you're doing with that data. Okay, so those are some reasons why we might want to use it. There's, of course, some possible downsides. And so I first listed here cost, complexity, and inconvenience, and then I immediately cross it out because this is kind of an old argument, right? So it used to be that to do this sort of visual data analysis in VR, that you needed, a $10,000 headset or $1 million cave, which is a surround screen display room kind of thing. You had to pay people to like maintain all of this equipment. You had to maybe go to another building or to another lab or whatever to use it. And so there was a lot of barrier to entry to using VR. That's not true anymore, right? Now you can run down to Best Buy and pick up a MetaQuest, and you can be doing this pretty quickly with kind of minimal inconvenience, minimal cost. There's still other possible downsides, right? So because you're standing, you're moving your body, you're wearing these devices that might make your eyes tired, et cetera, there's definitely opportunity for discomfort and fatigue with these technologies. There's accessibility issues. Not everyone can use them equally. It may be difficult to kind of get into the workflow of using this, fitting it into your own workflow. And then there's incompatibility, not only with your workflow, but maybe with the software that you're using or the data format that you're using or whatever. So those are still possible downsides. All right, so what I really want to focus on is kind of really a couple of decades of work on empirical evidence for the benefits of immersion. Why can we actually measure benefits for using VR technologies for visual data analysis, and can we say why they're happening? And so I put this one up here first. This is not my work, but this is kind of something that started me thinking about it. This was some work done by a guy named Kenny Gruchala, who still works at the National Renewable Energies Laboratory. And he was looking at oil well drilling and planning the paths of oil wells through the ground in order to get optimal production. And they had this kind of desktop 3D application, excuse me, which you see here on the left, and that used kind of typical mouse and keyboard input. It was 3D graphics, but it wasn't stereo, etc. And then he developed a version of that ran in a cave. And again, if you don't know what a cave is, you can kind of see it here. It's this kind of VR room that consists of multiple large screens that surround you and display stereoscopic graphics, and there's head tracking, so you can move around and see things from different points of view naturally. And so he ran a little study of experts doing this task of planning and editing these well paths, and found that people were faster, more accurate in the cave version, and that they preferred it to the desktop version. So that's a pretty good start, right? That shows that there's something going on here. But it's really hard to tell from this kind of A versus B study what it is that causes that benefit. So is it the fact that you're interacting with 3D input devices? Is it the fact that you're seeing stereoscopic graphics? Is it the fact that you have head tracking? Is it the fact that the screens are just bigger and there's more resolution, right? We don't really know from this study, but this is a pointer towards some possible interesting things. So we did something similar at my lab a few years later. I had a student, an undergrad, who was a caver. And so now I'm not talking about like VR caves, I'm talking about real underground caves that you go spelunking in, right? And so he had been mapping underground caves with, taking measurements of them and then creating 3D models of them. using 3D graphics. And so here's an example of what one of those models kind of looks like. And from this, he wanted to be able to do analysis. He wanted to be able to say, like, what's the slope angle at this point, or where might the water be draining from this cave, and things like that. Or does this passage connect to another one? And so we put these cave models into our cave, right? Into our VR cave, and we ran a study that was similar to Guchala's study, but a little bit more controlled. And so we used the same hardware in both cases, but in the left-hand condition, we were just using one screen of the cave. We turned off stereo and we turned off head tracking. So it was basically like a big desktop screen, right? But the interaction was the same in both cases. In both cases, you were using a 3D input device to kind of fly around this model. On the right-hand side, we kind of turned all the features of the cave back on. So you had head tracking, you had stereo, you had all four screens displaying data. And again, we found that for certain tasks, people were faster and or more accurate in answering questions about these cave models in the fully immersive condition, or the more immersive condition, than in the less immersive condition. Okay, so that's good. It still doesn't tell us everything that we want to know. So we really want to go deeper than this. So we want to answer questions like, what is it specifically about these immersive systems that can lead to higher effectiveness for visualization tasks or visual data analysis tasks? And then beyond that, what level of immersion do we need? So do we really need this kind of full-blown cave or a high-end head-worn display? Or could we use just like a big stereo wall, or what we call fish tank VR, which is like a desktop with stereo and head tracking, or like a very simple head-mounted display like a Google Cardboard? Is that enough to get some of these benefits? What level do we need? And really what we're asking is, how do the different components of immersion work together and independently to produce benefits? So what do I mean by components of immersion? Well, I've kind of been hinting at it, right? There's a lot of different features of VR systems that might be causing these benefits. So it could be that more immersive systems have a wider field of view. That's like the instantaneous visual angle that you can see of the world at any given time, or that they have a wider field of regard, which is the kind of the amount of surround that you have. So in the real world, I have a 360-degree field of regard, right? Because I can turn all the way around and look at everything in this room, right? In a head-mounted display, I have that same 360-degree field of regard, but on a desktop computer, I'm limited to seeing only a slice of the world, right? It could be because of higher resolution. It could be because of stereo graphics. It could be because of the presence of head tracking, or the quality of the head tracking, or the hand tracking, and on, right? So it's not just like physical hardware components of the display. It's also things like graphics quality, or level of detail of the model that you're displaying, or how real the physics are. All of these things lead to more realism, right? And that's why they're components of immersion. So we tried to do a little bit of like organizing of this space to help us to understand it. And so to illustrate this, I've got this kind of simple model up here of just the human-computer interaction loop, right? So when a person uses a computer, the person is down here at the bottom in this diagram. They manipulate some input devices. There's some software that takes the data from those input devices. It all gets interpreted. There's a model of what it is that you want to show to the user, and that model gets rendered onto physical display devices at which time the user sees it. And this is just a loop, right? So every time in VR that I move my head, I get a new view of the scene, right? Okay, so that's the basic loop. There's three types of fidelity that we can identify around this loop. So the first is on the left-hand side, the display. So the different displays have different levels of fidelity, or different levels of realism. So kind of at the low end, maybe I have just like a laptop screen, right? On the high end, maybe I have a head-worn display. This is the Vario XR3, which is kind of very high resolution, very wide field of view. It's got an inset of super high resolution for the central part of your vision, et cetera, right? So high display fidelity there. On the right-hand side, we have interaction fidelity. So how realistic is the interaction that you're doing? And so kind of at the low level, maybe I'm just pressing like the arrow keys on my keyboard to move around, right? that is nothing like moving through the real world. So it's very low fidelity. On the high end, here is a picture of something called the Virtuix Omni, which you might see in a mall near you to play VR games. And this is where you're making pretty realistic walking movements to traverse the virtual world. So you're turning, you're moving your feet, you can also crouch and jump and so on. So that movement is very much like the movement that we do in the real world, so it's high fidelity. And then finally, scenario fidelity. So this is all about like the model that you are displaying to the user. And so like the simplest example here is, there's just two views of the same scene, but the right-hand view has much better lighting, it has much better textures, it's got, it could potentially have more physics and so on. So all of those things increase the realism of the scenario. So if I take those categories of immersion, or let me define those more precisely here. So display fidelity, objective degree of exactness with which sensory stimuli are reproduced by a display system. Interaction fidelity is the objective degree of exactness with which real world actions are reproduced. Again, like walking versus using arrow keys. And scenario fidelity is about the objective degree of exactness with which behaviors, rules, and object properties are reproduced in a simulation as compared to the real or intended experience. So the key word in all of these is objective, right? It's about realism and you can measure it objectively. It's not about how real it feels, right? And then if I take those components that I listed earlier, I can now kind of reshuffle them, and some of them are display fidelity components, some are interaction fidelity, some are scenario fidelity. Okay, so that's kind of some theory that we can use. How are we going to do the studies that analyze what is the contribution of various components of immersion to these benefits that we want to measure? So we use an approach called mixed reality simulation. And the idea of MR simulation is that you use a very high fidelity system to simulate systems with lower levels of fidelity. And why do we want to do this? Well, we want to do it because A, I only have to have one system, and so I can do studies of lots of different systems with just one physical system. B, I can simulate systems that don't exist or that are unavailable, right? C, I can control the components of fidelity independently, and that's really what I want to do for my controlled studies. And D, I can perform direct comparisons of simulated systems, but I can also independently do different variables, right? I can have single factor or multi-factor controlled studies. There are some disadvantages. I mean, the simulator that you have, you can't simulate a higher level of fidelity than what it has. And it may be difficult to reproduce some elements of things. So like accommodation cues are hard to change. And people might question the results because you didn't actually study the real system, you studied a simulation of the system. But still, this has been a really profitable approach for us. And here's a couple of platforms that we have used. I already talked about the Vario XR3 on the right, which is kind of a super high-end head-worn display. We've also used a very high-end surround screen display. This is the Dive at Duke University, which is a 6-sided cave system. So you're kind of fully surrounded. It has really good computing and head tracking and stereo and so on. Okay, so let me stop and see if there are any questions at this point before I dive into some more results. Okay. All right, so yes, please.
Virtual reality highly threshold the benefits of like fresh augmented reality.
Yeah, so I don't know if everybody online could hear the question. The question is benefits of virtual reality versus the possible benefits of augmented reality. And I'm not going to talk about AR today, but we certainly are doing a lot of that in my lab as well. And the technologies are very similar. So most of the stuff I'm talking about, I think, would also apply to augmented reality. It depends on kind of what data you're viewing and how inside the data you need to be, right? So if I'm an architect and I'm doing a design review of a building, I probably want VR where the physical world is replaced by the virtual building, right? But if I'm doing visual data analysis of like that protein data that we saw earlier, and I can do it in AR and put it on top of my real desk and look around it, you probably get similar benefits in AR as you do in VR. So it all kind of fits in the same continuum. Good question. All right, so what I want to do is go through just another smattering of experiments that we've done over the years using this MR simulation approach to try to get more at the question of what is it about immersive systems that's good for visual data analysis, and what are the components that are responsible for that. So the first one is going back to this visualization of underground caves that I showed earlier. So we did a follow-up study, and we wanted to control 3 components of immersion independently here. So we had field of regard, that is the amount of surround that you have where you can see the virtual content. Stereo, on or off, and then we had head tracking, on or off. And we asked people to look at these were kind of simulated underground caves. They weren't from real data, but we asked people to do very difficult small scale spatial judgments within these models. So the part that you see circled here in the image is a little gap, and so there's this kind of vertical passageway or tube that is connecting 2 levels of this cave. Well, or it seems to be connecting, and the question is, does it really connect? So if you go down this, can you get to the lower level? And so you have to be able to judge, is there a gap there or not? And sometimes it's really close, and from certain angles it looks like there isn't, and certain angles it looks like there is. So you really need to get your view in the right place, and you need to understand the spatial relationships to see whether it's actually touching or not. And what we found in terms of display fidelity is that having wide field of regard and having stereo were both beneficial for this task independently. So if you could make the surround more, or if you could display in stereo, you actually got faster and or more accurate answers to these questions. I'll come back to that in a second. But another example, very similar, we were doing a collaboration with someone in biomechanics who was looking at the tracheal systems of beetles, which is pretty fascinating. But here on the left is an image of the example 3D model that we're using. It's super complicated, very organic, right? No right angles anywhere, all sorts of weaving in and out. And again, you had to do these difficult spatial judgments, right? So like how many branches are there coming off of this tracheal tube? Or does this tracheal tube connect to this other one, right? Similar to in the cave example. And we did another study, another controlled study of, I believe, the same 3 components, field of regard, stereo, and head tracking. And what we found here was overwhelmingly that stereo had the strongest effect. If you could turn on stereo, you could get better answers to these questions more quickly. Okay, so those were display fidelity results, and now interaction fidelity. Coming back to both of the previous studies that I mentioned, as I said, we varied head tracking in those studies as well. And again, in both studies, we found that having head tracking as a method for positioning your viewpoint could also be beneficial for certain of these small scale, difficult spatial judgments. And this makes sense, right? If you really need to have your view very precisely in a certain location to be able to see whether there's a gap or not, like in the cave data, it's much easier to do that with these natural head movements than it is to do it with a mouse or a joystick or any other sort of unnatural input. Here's another example from interaction fidelity. So we were interested in manipulation, 6-degree of freedom manipulation of data. So in other words, moving it, changing its position and orientation. And the task that we looked at was aligning with 6 degrees of freedom some data with a target. With another model. And so in the upper left-hand image is an old study that we did where the data that we were manipulating were just these kind of 3D letters. They were like 3D shapes in the shape of the English alphabet. And you had to take like this R on the left and align it with the R on the right by translating it and rotating it. And we compared kind of a direct manipulation with a 6-degree of freedom input device in your hand versus a desktop style manipulation that used a mouse and a keyboard. And we found clear advantage of the 6-degree of freedom input device, which is a little bit surprising because like a mouse is way more precise than a 3D tracker, especially in 2006 when we ran this study, right? But the fact that you can change all of them at once and do it in a natural way means that you can do it faster and more accurately with the 6-degree of freedom input device. So why is this important? So nobody's going to be visualizing J's and R's, I don't think, in this room. But you are, this task of aligning objects with 6 degrees of freedom is important for visual data analysis. And in fact, we're talking with Haichao about that in our project, where we want to see if a certain model is identical to or has differences from another model of the same 3D data. And so that's the picture on the bottom right here. And we know that we want to do this with a integrated 6 degree of freedom interaction technique, a natural interaction technique. But the knock on all of those, as I said before, is that they may not be precise enough, right? It may be hard to do very exact placement using this kind of in-air hand-based manipulation. And so we've been working on precision alignment techniques that are still feel natural, but that allow you to do very precise movements with 6 degrees of freedom. I don't expect you to read all of this, but these are just some other examples of benefits and limitations of natural interaction, of kind of higher fidelity, higher interaction fidelity. So things like, for example, at the bottom, we did a study of aiming tasks. And we found that if you could aim, like with a gun, for example, using a natural, again, hand-based 6 degree of freedom device, that can have better performance than using a mouse to do the same aiming task. But in all of these categories of tasks, there are some advantages of this higher interaction fidelity. Okay, but it's not always true, right? So I don't want you to get the impression that more fidelity is always better, especially for interaction. And so here's a fun video to watch. If you've never seen this thing before, this is called a virtue sphere. It's a fairly old at this point attempt to do natural travel, natural walking in virtual reality. And so this person is standing inside like a human-sized hamster ball, which is on some rollers and has some sensors. And in order to move in the virtual world, you have to kind of walk forward and spin this ball around you. And you can, of course, walk in any direction and turn and so on. But if you watch this video, you can see that it's pretty hard to control. This thing weighed about 600 pounds. And so getting it moving was pretty hard. Stopping it was also pretty hard. And changing direction was pretty hard because it had lots of inertia. And so although the fidelity of this interaction, it's much closer to real walking than using like a joystick, right? It's really hard to use. And so we did a study of this just to kind of prove the point. And so on the left here, we're looking at accuracy of walking movements. And on the right, we're looking at the speed of completing a walking path. And we compared the Virtue Sphere to a gamepad, like what you would do on your Xbox, and to just regular real walking that is tracked in a room. And you can see that the Virtue Sphere is much, much worse than both of these other techniques in both of these measures. And here's kind of an analysis of the fidelity of these three techniques. So on the left, we have the gamepad, and things that are red and orange and yellow mean lower fidelity. Things that are green mean higher fidelity. And we kind of analyzed each kind of component of interaction fidelity, which I won't go through in detail here. And you can see that the gamepad technique is on the whole pretty low. The real walking technique, as you might expect, on the whole is quite high fidelity. And the Virtue Sphere is somewhere in the middle. So if we had kind of this linear relationship between realism and performance, we would expect the Virtue Sphere to be better than the gamepad, but worse than real walking. And as I showed, that's not what we found. So we have this kind of hypothesis of like an uncanny valley, basically, right? So getting more real in terms of interaction, and especially walking type interaction, can actually be worse up to a point. But when you get very real, maybe it's better. And so we have this kind of U-shaped curve that we hypothesize. So our study showed that for sure. We did a meta-analysis of a bunch of other studies of locomotion techniques in VR, and they kind of all showed this similar pattern, right? So things that were moderate fidelity were often worse than things that were low fidelity. And so why is that the case? I mean, if you think about it, it kind of makes sense, right? So on the low fidelity side, we have complete freedom to design the technique to do it, to work any way we want, right? So these gamepad style interfaces or mouse and keyboard style interfaces or whatever, they don't have to be realistic. So the designer can make them more usable by tweaking them, right? Tweaking the mapping between the buttons and the joysticks and so on and how you move. The high fidelity ones are just like what we do in the real world, so they can be very familiar and easy to use as well. But the moderate fidelity ones, they give the appearance of being easy to use, right? So the virtue sphere, when I explain it, right? Okay, get in this thing and walk. But then you try to do it and you find out, well, it's kind of like real walking, but it really, in a lot of ways, it's not like real walking at all, much harder to do. And so we have to be careful. Just adding some level of realism is not always good enough, especially in this area of interaction. Okay, so that was a little bit of a sidebar. Finishing up kind of the example studies, here's the one study that we did on simulation fidelity. So our scenario fidelity, I should say. We used to call it simulation fidelity. It's an old slide. And here we were doing a training task. We were trying to train military users to visually scan a street or a set of buildings for possible threats. And so you can see in each of these images near the red circle, there's a person with a gun, right? And so you had to do this visual scanning path and make sure you didn't miss anything, but make sure that you found the threat quickly. And we trained people at different levels of visual realism. So you can see as these pictures go from left to right, we have a pretty unrealistic world on the left, all the way to a very realistic world on the right in terms of model detail, in terms of texture mapping, in terms of lighting, et cetera, et cetera. And interestingly, what we found was that when people trained in the high level of visual realism, they were actually better at using the visual scanning strategy in the real world afterwards, because what they trained in was more similar to what they were going to see, right, when they did the real world task. Okay, so I want to try to summarize all of these findings, or a lot of the findings that came from our lab. We did dozens of studies along these lines over the years. And so this is a pretty complicated visualization, and probably some people in this room could design a better one. But let me try to explain what I'm showing in this visualization. So we have the three categories: display, interaction, and scenario fidelity or simulation fidelity. And for each one, I've got a bunch of different lines. And what a line means in this case is we're showing something with low fidelity on the left is significantly worse than something with high fidelity on the right. And in this case, the S means it's for a spatial understanding task. And the thickness of the line means kind of how many results do we have that demonstrate this sort of significant difference. Okay, so this is like 4 results that show that high fidelity is better than low display fidelity for visual spatial understanding. Okay, so here's another example. This is a negative example. This is showing that something with kind of moderate to high fidelity display fidelity is significantly worse than something with low fidelity for a visual search task. And we have maybe 2 results of this sort. Okay, so now let me show now all the display fidelity results. Okay, so again, this is from dozens of studies over the years. And what you can see is that, number one, most of them are positive, right? Most of them show that higher fidelity is better for lots of different tasks, and some of those results are replicated many times. And then there are just a couple of negative results, right? But they do exist. Here are the results for interaction fidelity. Again, almost all of them positive, but what stands out here is this thick red line that shows that moderate fidelity interfaces can be significantly worse than low fidelity interfaces for travel tasks. That's those locomotion tasks I was talking about just a second ago with the virtue sphere. So that's a very replicated result. And then we only did really the one study on simulation fidelity, so I show that here. Okay, but this is kind of a visual summary of what we found over many years. And so we're basically saying that there is lots of empirical evidence that higher levels of immersion, higher levels of fidelity, especially for some components, can really benefit visual data analysis tasks, especially when you have complex data sets, especially when you have difficult spatial tasks. What these studies don't show us is really what the mechanism is inside the brain, right? But we hypothesize that, having good visual depth cues like stereo and having body-based cues, proprioceptive cues as you're moving naturally in these environments lead to improved spatial understanding, and that having natural navigation and manipulation techniques reduce mental workload, like I said a while back. And that frees up your cognitive resources to do the actual work that you're in there to do, to analyze the data. So some take-homes: higher fidelity very often results in higher effectiveness. Increasing fidelity doesn't always improve. And so what I didn't show on that summary slide is all the non-significant results, of which there were many, right? I only showed the significant ones. But on the other hand, we saw very few cases where higher fidelity was detrimental. The best cases seem to be where we have difficult and complex visual spatial tasks, where we're doing learning or training, or where we're doing interaction that has high degrees of freedom. But again, the caveat: moderate interaction fidelity can be problematic. Okay, so that's kind of a summary that hopefully convinces you, at least to some extent, that VR for visual data analysis has some grounding, some foundation that demonstrates that it can be beneficial. But I don't think, simply putting your data into VR and looking at it and maybe doing some simple interaction with it, that's not all we can do with VR. And so I want to close by just talking about a couple of other potential advantages of using VR. And so one is that you can have innovative and natural interaction opportunities. And so here's a fairly old example. This is something that we did called Volume Cracker. This is not actually using immersive VR. This is on a desktop, but and that was because we couldn't do really good bare hand tracking back at that time in an immersive setup. But you could certainly do this in a head-mounted display. So the idea here is you have volumetric data, and you want to. The problem with volumetric data is it's hard to see inside, right? And so the typical approach is to use like a cutting plane to see different cross sections of the data. But it can be hard for users to really understand what they're seeing with cutting planes. And so our idea was, well, maybe we use this metaphor that the volume data is like a book, and what we can do is like crack open the book, and we see two cross sections from the same part, but we can also just flip through the book and see the cross sections moving. And so that's what this volume cracker was intended to do, and we did it with this bare hand approach, as well as a bare hand plus a joystick that you can see here. And we were able to find that our science collaborators could in some cases better understand their data through an approach like this. Okay, so this is something that you can do in VR that is another potential advantage. Here's another example, much more recent. So Leo, sitting in the audience, has been working on multi-scale navigation through these data sets. So a lot of these data sets have lots of data at different levels of scale. So you want to see like the whole part, but you also want to see very fine details that are hidden within the part. And so we've been thinking about this as multi-scale data. And so here's the kind of typical cutting plane approach that I was talking about before. But to go inside, what we do in this interface is we divide the data into octants, and we just choose an octant by pointing at it. And that scales you down to the level of scale of that octant and allows you to visualize it. But it also gives you some information visually about where that data came from in the whole model, right? So you can hopefully stay spatially oriented as you zoom in or as you scale down to see the details, but also keep in mind the bigger picture of where these details exist. So that's kind of interesting. And then besides interaction, there's opportunities in VR, I think, to do better collaboration, right? And so this is not a visual data analysis example, but this is an example of people inside a virtual environment working together on data and being able to kind of more naturally view it and communicate about it and annotate it together. And so here they're actually looking at data from scholarly literature. It's like little annotations about different papers. And we have people kind of in the room together. So you see there's the user whose view we're seeing, plus another user who are co-located, and they can all see the same data and interact with the same data. But there's also people who are remote, who are also in the same space, the same virtual space as avatars, equally able to communicate, to point at things, to interact, to annotate, and so on. And so I think for visual data analysis, there's a lot of opportunity here in VR. And can you do these different tasks on a desktop? Yes, of course, you can. But the communication is likely to be more limited, right? Because you're not in the same space together and able to work together naturally. So again, you have to use more of your mental resources to communicate and to be aware of what other people are doing. Maybe in VR, we can free up some of those cognitive resources to allow people to collaborate more naturally. Okay, and then finally, Gio's work. This is another question about collaboration is how can we collaborate asynchronously, right? So that was synchronous collaboration. How can we collaborate across time? And so the kind of first approach that we're doing here is thinking about how can one user provide a guided tour through data to other users who will view it later. And so I'll let this play, but here's some data.
My name's
right?
Alexander
And
Juvenelli, and
it's a
I am one
recording
of the
an
designers as part of the
expert
Direct
giving
Ink
a
Write
guided tour
initiative.
through data.
And today I wanted to take a closer look at this particular print scan that you provided us. And I wanted to go over this particular corner here where we can see an excess amount of ink. So, at first,
All right, so let me explain what just happened there, right? So we have this recording of this expert giving a guided tour, and I'm watching, I can see their recorded avatar, I can hear what they're saying, I can, see where they're pointing and so on. But what happened was that at a certain point in the tour, the expert pointed to something and pressed a button, indicating this is something important that the viewer should pay attention to. And so all we're doing is very simply like pausing the playback automatically at that point. And the user, the viewer then has the opportunity to like go look at that and understand what it is that the tour guide is trying to point out. And then once they feel that they're ready, they just click on the avatar of the tour guide and the tour continues, right? So it's a way to like help ensure that the observer is paying attention and that they're paying attention to the right stuff, right? They're following along with the tour guide. And if I let this play further, you would see that when the tour guide moves the cutting plane, it's the same thing. The observer then has to move the cutting plane in a similar way. When the tour guide uses this multi-scale navigation technique to scale down, the observer has to do the same thing in order to continue with the tour. And so our thought is that this kind of interactive asynchronous tour will allow people to remain more aware and get deeper understanding of what the tour guide was trying to get across. All right, so I think we're pretty much out of time, so I'm going to stop there. But I hope that this has been some food for thought about why VR is useful for these visual data analysis tasks. And I'm happy to take questions. Thank you.
Yeah, and I really like that. It helps me a lot to think about it in the categorization that you read. Can you comment a little bit more about, so you touched a little bit on like the things that we came to in the real world ultimately, right? That's what VR is good at. Has there been a lot of experience with when we sold this initially, we were making a big fuss about, right? You could have superpowers, right? We see all these movies where it's like, oh, like Superman has X-ray vision, right? Again,
yep.
But then when we were thinking about, okay, what would that actually mean? It was like, it's not quite clear that my brain is really ready for X-ray vision, right? And what would that mean and how would I look at it, right? So has there been, where's that limit of like, how far can I push like the real world versus what I could imagine to be able to do?
Yeah, so for people online, if you couldn't hear, the question is, what about going beyond realism, right? So VR can allow you to do things that you can't do in the real world, have superpowers basically, and do those have benefits, or is that just going to make me more confused? Is that kind of a summary of the question? So yeah, we've done some work on that as well, and we looked at it specifically in the context of locomotion again. So as I said, if we make locomotion interfaces kind of slightly more realistic, they're often worse. But with locomotion specifically, you can give people lots of superpowers, right? You can make them fly. You can allow them to, make great leaps with a single bound. You can allow them to have much higher velocity of locomotion than they could in the real world, and so on. And so I think those are all opportunities to overcome those limitations of moderate fidelity. And we've shown that, in some cases, giving people these superpowers does allow them to interact in a more effective way, even though there are still some limitations, right? So you can kind of mitigate or overcome those limitations of not quite perfect realism by letting people do things, more effectively through superpowers, right? So I can navigate much more quickly, for example. So that's definitely an advantage of VR that I didn't touch on here. We don't have to be limited to trying to get as close as possible to what we do in the real world. That's a really good point.
I have a question, but there's some apparent questions on the virtual audience too, so I don't know how it goes. But my point is, do you have like time trial studies of a first-time novice VR person, and then with that same system, how they get more efficient and adapt to these superpowers that they have?
Yeah.
Track that.
Yeah, so I guess the question is kind of about longitudinal studies of as people become more expert at using VR, how does the effectiveness change? So those are really hard to do. And so most of our studies are not that. Most of our studies are really of almost purely novice users, right? And so it doesn't quite capture the real world situation of someone whose job it is to do this visual data analysis in VR. So I think definitely more work needs to be done in that area. I mean, one hypothesis might be that VR can get people up and running more quickly with these sorts of tasks because it's more realistic, it's more natural. You don't have to learn all the controls. You just do what you would normally do to look at this data. So what we don't know is whether the benefits of VR persist or even get better as you gain more experience with it. I mean, there are lots of kind of expert interfaces out there that are almost impossible for novices to use, but if you use it every day for your job, you can get really good at it, right? So maybe VR is a good way to get people up and running quickly and to make contributions more immediately in visual data analysis tasks. That would be my guess.
One question on the line is, wearable gear with haptic feedback for VR have any positive impact?
So I couldn't quite hear all of that.
Does wearable gear with haptic feedback for VR have any positive impact?
Okay, so does wearable gear with haptic feedback have positive impact? That's not something that we've studied in my lab directly. But again, I would posit that haptic feedback can be really good for when you need to do, for example, these alignment tasks, right? If you're trying to align one data set with another. If you're doing it in free space with no collisions and so on, you have to rely purely on visual cues and your ability to move your hands. If you have haptic feedback that can where you can feel the data snapping into place, for example, I think that could potentially be beneficial, but I don't have results on that here.
Yeah, I have a question. Sort of towards barrier of entry. So let's say I'm a researcher, I've got a big budget, so the cost of equipment is no thing, but I don't have a VR guy on my team. Can you talk a little bit about how we could visualize our data sets if we're kind of novices to VR?
Yeah, how can you visualize your data sets if you don't really have a VR expert? So that situation has gotten a lot better, I think. So it used to be the case that you really needed to have not only the expert to kind of get you going, but to maintain your system and to, to upgrade your system and all of that stuff. So definitely on the hardware front, as I said, right, you can run down to Best Buy and pick up a Meta Quest today. And that's, it's designed for a person with no knowledge whatsoever to set it up in 10 minutes. It's the software side that I think still needs some work, right? And software and data formats. But there are definitely more and more kind of open source projects or whatever that allow you to transform your data easily to the right format. And then there's an application that runs on the headset or whatever that allows you to load it in and do all the basic stuff. So view it, move around it, rotate it, zoom in and out, all of those sorts of things. So I think to just initially see your data, there's still some work to be done on the software side, but it's way better than it used to be, and will continue to get better as more and more people are doing this sort of work.
Let's see. I think we had one more question online that we could take. Was there one more in the chat?
There are two.
Let's see. Can hold them up here. I'll let you read it. Yeah.
We did this one. Did we do this one?
Sure.
For overcoming
Yeah, so it says, with regard to display fidelity, does a technology like holographic projection have a chance to provide value over headset VR methods anytime soon, if at all? No, not anytime soon, I would say. So kind of the Star Wars vision of having kind of these 3D holograms that appear in space in front of you, where you don't have to have any headgear or glasses or whatever to see them. People are working in those directions. There are prototypes of such things at various levels, but it's pretty far out, I would say, still in terms of making a real world impact. So headsets, I would say, are the best, the sweet spot right now in terms of cost and convenience.
All right, well, I think we're at time, so let's go ahead and wrap up. Thanks so much, Doug, for a very interesting and engaging talk.
Thank you.